So in our last lab, we constructed the parallel axis theorem, which said that the rotational inertia about any parallel axis is equal to the rotational inertia about an axis through the center of mass plus a quantity mh squared, where m was the total mass of the object and h was the distance from the center of mass to the parallel axis, the new parallel axis. Right? And that would allow us to convert the rotational inertia about the center of mass to really any other axis. Right? And experimentally, that's what we found. But we actually have enough physics and enough calc to be able to figure this out theoretically. So what I'm going to do in this video is to derive the parallel axis theorem, and we'll see if we get a result that matches what we saw in the lab. So here is just an irregularly shaped object. Let's say its center of mass is there. I'm just picking a point for us to use, right? Now, we can impose a coordinate system on that point. So notice here the center of mass is at 0, 0 on this coordinate system. But our actual axis of rotation is at point P. This is our actual axis of rotation, so it's going to rotate about that axis. Note that point P is a distance h away from the center of mass. So there's our h, right? Now, for reasons which we will see in a moment, because this is a two-dimensional thing, I'm going to see here how much of h is horizontal and how much of h is vertical. Well, that much of h, which I'm going to call A, is the horizontal component, and that is how much of h is vertical. That's the vertical component, if you will. Right? So that will allow us to relate A, B, and H together if we need to. Now, in order to do the integral, we need to break this thing up into a bunch of little mass increments, like, for example, one up here. Just going to pick one up here. It's got a mass of dm, a vanishingly small infinitesimal mass, right, that we are going to integrate sum over the entire object. That little mass increment is has coordinates, which I'm going to call x and y. This is the x-axis, that's the y-axis. Okay, so the coordinates of this are x and y. The coordinates of P are a and b. The coordinates of the center of mass are 0 and 0. Now, the little mass increment is a distance we shall call little r away from the actual axis of rotation. Right, like we've been using. Little r is the distance from the axis of rotation to our mass increment. We can break little r up into horizontal and vertical parts, which is going to be something we're going to need for the proof. Okay, so here's the horizontal part of r. Well, what is that? Well, notice that the whole thing here is x, right? And this part of it is a. So what's that part? Yeah, it's x minus a. You okay with that? The length of this piece has to be x, which is all the way out here, minus a, right? And that's what's left. The vertical part, well, the entire vertical is y. This part of it is b. So this part would be y minus b. See the little right triangles we're making here? So we're breaking these up into their perpendicular components, if you will. And then one more thing. How far away is the mass increment from the center of mass? A distance which we will call r. Right? And if you notice, r has perpendicular components x and y. Right? So each of these little distance things that we've written up here, h, which is the distance from the center of mass to the actual axis, the parallel axis of rotation, right? We know the perpendicular components, or the coordinates, if you will, are a and b. Little r is the distance from our parallel axis of rotation to the mass increment. That's x minus a and y minus b. And capital R is the distance from the center of mass to the little mass increment, right? And that has perpendicular components of x and y. Now we'll pull this back up and come back to this one where we need it, okay? But we now have enough info there to do some fancy stuff and do the calculus proof here. So the rotational inertia about point P, right, about our parallel axis, see P for parallel, is the integral of all of the r squared dm's. R being the distance from our new parallel axis of rotation to each little mass increment. But if we look back here, what is r squared? Well, there's a little right triangle here. So couldn't I rewrite r squared as x minus a squared and y minus b squared? Couldn't I do that? See that little right triangle in the original diagram? And this is all inside of the integral, so these big brackets keep it all inside the integral. Well, next step, we're going to square both of these. That's what we get. X squared minus the integral of the quantity. X squared minus 2ax plus a squared plus y squared minus 2by plus b squared, all with respect to mass. Okay. Now, because these are all additions and subtractions, I can use commutative and associative properties and kind of rearrange them. And I'm going to rearrange them in a way which will be convenient for us in a few steps. So I moved the y squared over here and gathered it with the x squared. I left the minus 2ax here, the minus 2by here, and I moved the a over to the right with the b squared. Right, so I just changed the order and the grouping. Okay. Now, remember that when you're taking the integral of a sum or a difference, right? The integral of a sum or a difference is the sum or the difference of the integrals. In other words, I can take an integral of each piece one at a time, right? Like this. Notice how I put dm on each one of these integrals. So this is the integral of the x squared plus y squared with respect to mass. Minus, now I pulled the 2a outside because it's a constant, so I'm doing an extra little step here. Right? 2 and a are constants. Right? And so that's 2a times the integral of x with respect to m. Pulled out the 2b because those are constants, so minus 2b integral of y dm plus the integral of the quantity a squared plus b squared with respect to mass. But let's take a minute to look at the two inner integrals. Now, don't worry about the 2a, which is just a constant. Have we ever seen something like the integral of x dm? The integral of the distance with respect to mass? Now, we know that the rotational inertia is the sum of all of the mr squareds. But we did have something that was the sum of all of the mr's, or the mx's in one dimension, or my's in 2 dimension, or mz's in 3 dimension. Anybody remember what that was? Yeah, this is essentially the position of the center of mass integral. Right? This is the integral we have to use to find the center of mass. And since it's x, this is the x position of the center of mass. Technically, there's an extra little mass term in there as well because it's 1 over the total mass times the integral. But right, at least the integral gives us the position here. And if you look back at the diagram, what was the position of the center of mass? 0, 0. So this is 0. Right? So that goes away. Likewise, this is just the position vertically of the center of mass, which is also 0. So those two terms drop out, and what we're left with is this. The rotational inertia about the parallel axis is the integral of the quantity x squared plus y squared dm plus the integral of a squared plus b squared dm. But if we look at the diagram, what would x squared plus y squared be? X squared plus y squared, isn't that capital R squared? And isn't a squared plus b squared little h squared? Little Pythagorean theorems. And now look what we have left. We have the integral of r squared dm, capital R squared dm. Well, that's the integral of all the little mass increments around the center of mass. And since it's around, since r squared is the distance from the center of mass to the mass increment, isn't this just the rotational inertia around the center of mass? With me so far? So this is the rotational inertia about the center of mass. And then over here, well, h, which is the distance from the center of mass to our axis, that's a constant for any single axis that we're looking at, right? That's a constant distance. The mass increments move, but these two things don't move, right? Which means we can pull it outside of the integral. So h squared, integral of dm, what's the integral of the sum of all of the little mass increments? It's the total mass. And there we've done it. We have theoretically derived the parallel axis theorem, which again says that the rotational inertia about any parallel axis is equal to the rotational inertia about the center of mass plus the mass of the object times h squared, where h is the distance from the center of mass to the new parallel axis. Right? And this will allow us to convert from one to the more general one without having to redo the calculus. Right? So this is an expression that we can now use, and we see that it works both theoretically and, in fact, really works because that's what we got out of our experiment. Within about 4%, right? Which is still pretty good considering what we were doing. Right? So this is an accurate way to find this. So now we have to start applying all of these things that we've been learning about rotational inertia of continuous objects and this beautiful parallel axis theorem. So here's a little problem, which we'll do a couple different ways. We've done this one before, actually. We can deal with these as point masses. Here's two equal 2 kilogram masses separated by a distance L. It's a thin massless rod, so the rod doesn't count in this case, 4 meters long. What would the rotational inertia be about an axis perpendicular to the rod and through one end? Like that. See the new axis? Okay. Well, if we just did this using our rotational inertia of point masses equation, which would be the sum from I equals 1 to 2, because we can treat these as point masses if we go from center to center, of all of the mi ri squareds. Right, that would be m times r1 squared plus m times r2 squared. The only reason I don't put a 1 and a 2 on the m's is because they're the same. Right, if 1 was 2 kilograms and this was 4 kilograms, I'd have to do, you know, a 1 and a 2, or an m and a 2m, or something like that, right, to deal with them being different. Well, if this is our coordinate system, right, what is the distance from the axis of rotation to this first point mass? It is 0. Right, so that drops away. And how far away is our second point mass from the axis of rotation? It is the full distance L away. So the rotational inertia ends up being ml squared. And if we plug numbers in, we get 2 kilograms times 4 squared, right, which is 32 kilogram meters squared. So there's the old way of doing the problem, right? But we could also use the parallel axis theorem. Now, if you look back in previous work, we found the rotational inertia about the center of mass for this very situation as being 1/2 ml squared. The total mass, capital M, is 2m, if we call that m and m. And h is the distance from the center of mass, which would be right here in the center, to the new axis of rotation, the new parallel axis of rotation, which is 1/2 L. So, square, right, that's 1/4 L squared. Simplify, 2 times 1/4 is 1/2. 1/2 plus 1/2 is ml squared. And of course we get the same answer. Now, I would say in this case, method 1 is easier, right, if we just treat them as two point masses. But I wanted to show you here that the parallel axis theorem, which, yeah, in this case is a little more complex, right, is also results in the same answer. We're going to eventually do ones which wouldn't be so easy to do without the parallel axis theorem.